Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting architecture called as Restormer, which is basically an efficient transformer method for high-resolution image restoration. This is an old paper. This paper was accepted in CVPR 2022, but it is still interesting to look at how they modeled this interesting problem. The paper obviously is very well cited, some 3,000 plus citations to this paper. So let's look at this Restormer architecture. So what is the architecture of this restoration transformer or restormer? Right now, this transformer is actually called as restoration transformer because it helps in image restoration. Image restoration is the task of removing degradations from an input image, for example, denoising or deblurring, removing raindrops and things of that kind, right? Handling for motion-based blur and so on. Okay. So now, if you typically used a standard architecture, standard transformer architecture for transformer, the standard transformer architecture actually has quadratic complexity in terms of number of inputs. So if you were really modeling every pixel as an input with the image size of h cross w, h being the height and w being the width, the transformer would have like quadratic complexity, h square, w square, right? To avoid that, they come up with this architecture. You see the architecture here on this slide. And the main key idea in this architecture is do not do self-attention computations across the h cross w spatial dimension, but actually do them across or along the channel dimension. Okay. So therefore, your attention matrix is no longer going to be h w square or other h square w square, but it's actually going to be just c square. And that basically is really the key idea of this paper. Okay. However, let's look at the detailed architecture. So in this, let's look at the input and output first. So input is the degraded image. The output is the restored image. As you can see, it actually has slightly better quality than this one. I'll show you more examples in the next few slides. Okay. And since the input output is basically of the same size, therefore it has to be an encoder decoder transformer. So therefore it uses an encoder decoder transformer, and it uses a 4-level encoder decoder transformer. So this is level 1 right at the top, level 2 that you see here, level 3 that you see here, and then level 4 is right at the bottom. Okay. So it is more like a unit style architecture in that senses, but obviously using transformer modules in that senses. Okay, it also has this refinement module at the end. So it has a 4-level encoder decoder transformer plus refinement module at the end. These 4 levels basically have like 4 layers here, 6 layers here, 6 layers here, and 8 layers here in that sense. And obviously in the decoder side as well, you'll have like 6, 6, 4 in that senses. Now this refinement module actually has like 4 layers of transformer. Okay. Now you also see that the input image basically obviously has 3 channels. But then across these different levels, the number of channels change. So number of channels are increasing. Here there are like 48 channels, here 96 channels, here 192 channels, 384 channels, and so on. So to be able to do downsampling, so basically there's downsampling going on the encoder side, as is usual in any encoder decoder transformer module, right? For images. So the downsampling basically means your h cross w is becoming h by 2 cross w by 2, and so on, right? So downsampling is basically done using a pixel unshuffle mechanism. What this basically means is that with your h cross w image is you have to reduce the height and width by 2. So what you do is to really take the remaining pixels. So so you're reducing the pixels by 4 times totally. But what you do is to really take all of those values and stack them vertically, thereby increasing the number of channels in your image. But then, you're basically reducing the overall width and height of the image. So obviously, if you just do that, then you would be left with, 4 times the depth. However, they further do one more operation, so one more convolution operation, so as to basically reduce it to 2 times the depth, so rather than making it 4 times the depth. So that's that basically. So that is how the downsampling and the upsampling operations are done. Similarly, while upsampling, you would expect that, hey, if you take the h by 2 w by 2 cross 2c image, you would basically end up with c by 2 channels because you have to spread them out, spread the pixels out. However, you end up with c channels in that senses by doing an extra step. Okay, so that's basically how this pixel unshuffle and pixel shuffle works. and that basically leads to a downsampling and upsampling that you see in this multi-level network. Now, to talk a little bit more detail about each of these transformer layers, it basically does self-attention and feed-forward as is usual. But self-attention is changed to MDTA, which is multi depthwise convolution-based head transposed attention. Okay, so multi depthwise convolution-based head transposed attention. Okay, so it's also self-attention in some ways, but it's a slightly different self-attention, as I'll talk about in detail in this yellow block. Okay. Now, the other part is feed-forward network, and the feed-forward network is also changed slightly, as you can see here. It's basically called as the gated depth-wise feed-forward network, and we'll talk in detail about this block as well. Okay. However, let's convince ourselves about the larger multi-level architecture. So you see there are these skip connections as to ensure that the encoder helps as much in restoration on the decoder side or reconstruction on the decoder side, all of these skip connections. There's also a skip connection right at the input, which basically helps decode the final output. So that's basically that. And now let's talk about this multi-depth-wise head transposed attention. So here you basically take the input image, you basically process it through a 3x3 convolution so as to get C channels. Now, if you look at any of these transformer blocks, basically each block has this MDTA. What it does is to basically take your input. The input will have some height and width and some number of channels. It basically normalizes the image, Z-score normalization, standard normalization. And then you do the standard 1x1 convolutions so as to basically have cross-channel context, aggregation of cross-channel context. So basically, these are standard 1x1 convolutions just to have good information sharing across different channels for the same pixel. Okay. After that, you apply 3x3 depth-wise convolutions. Now, what does this mean? This basically means that you have 3x3 filters and you're exchanging information in the local neighborhood of these 9 pixels. But remember, they operate for every channel separately. So essentially, these 3x3 filters are actually not shared across channels. So that's what depth-wise convolution means, that you have this channel-wise aggregation of local context. For each channel, it happens separately. Okay. So after that, what you do is to reshape these matrices. You call these now as QKVs. Obviously, you use different set of 1x1 and 3x3 filters so as to basically have QKVs, query key values. Okay. And then you basically reshape these so that you basically do the self-attention operation not across the height versus width dimension or the spatial dimensions, but across the channel dimensions. Okay, so leading to a C cross C attention matrix. And basically all of these operations that you see here are the standard transformer-based self-attention. So essentially you do QK transpose, getting the self-attention matrix, then you do multiplication. You obviously also do normalization, so divide by a learnable alpha, and then you apply a softmax on top of it, multiply by values so as to basically get the final output. You do a 1x1 convolution so as to basically get as many channels as you like. Okay, so that's basically that. Now the gated gated depth-wise convolution-based feed-forward network. So the way so in the standard transformer, the feed-forward typically works in 2 parts. There's a dense layer, so there is a upsampling which happens in some ways. You basically transform from a dimension D to 4 times D typically, and then you transform it back to D dimensions. So there are like two dense layers there, right? So that's basically 2 dense layers, two dense layers with 2 matrices A and B in some ways, right? So you have the same thing happening here. Now you can basically, and these are position-wise feed-forward network, right? So therefore, you could basically also think about it as 1x1 convolution for that matter, because 1x1 convolution is really position-wise dense network anyway. Okay, so when you get the input, you're basically doing 1x1 convolution, and this time you're doing it along the spatial dimension in that senses, right? Post that, you do 3x3, depth-wise convolution, which basically ensures that you have enough local context information sharing, this is done again across separately for each of the channel dimensions. So now there are 2 paths that you have created here. One of the paths is actually to act as a gating mechanism. So you apply the ReLU here, so as to basically act as a gating mechanism. ReLU, as you know, basically clips or clamps all of the negative values to 0. So that's basically that. And you have the non-ReLU path coming from here. So basically the information channel in that senses, this is the gating channel in that senses. You do element-wise multiplication, and the output that you get, you essentially do the second dense layer in that senses also can be modeled as a 1x1 convolution in that senses, because the position-wise second dense layer in that senses, right? And that's the output of your gated deconvolution feed-forward network, right? So two basically, two or three interesting things here. There's a multi-level encoder-decoder transformer. There is a multi-depth-wise head transposed attention layer. There's a gated depth-wise convolution-based feed-forward network layer, okay? Now, the other interesting thing that they do while training is to basically ensure that they do progressive learning. So more like curriculum learning. So they start with small patches and large patches in early epochs. And then in the later epochs, they actually start to increase the size of the patches. As they increase the size of the patches, the batch size has to be reduced so as to fit in the RAM nicely. Okay. So that's basically the architecture of the restoration transformer. Pretty simple in today's world to understand, right? So how does Restormer perform? So, you can see some results here. So this is for image deraining. Here is an image with a lot of rain here, right? And these are the results. So this is basically the, the reference image without the rain, essentially, right? And this is with the rain in that senses. And you can see different kinds of models, derain, semi, many models basically showing you results out there. And when you basically see the final output from the Restormer, sorry, I've clipped, the names of the models got clipped from here, but they're all different models. The last one is Restormer. And what you see is that the Restormer basically really gives you an output image, which is very similar to this input patch. This input patch comes from a small part here somewhere, right? So from this part somewhere, this patch basically is restored very nicely, from this large, from this really weird rainy patch, okay? Now, the other example here is single image motion deblurring. So this is a motion deblurred image. And you can see, you cannot really read the number plate of the car. So this is the original image, but this is the deblurred image. This is the image which is given as input, and Restormer basically gives you a really, really good output, helping you figure out the number plate nicely. This is another task. So it's called as dual pixel defocus blurring. So what happens is when you're trying to do portrait photography, where the object is very close to, the camera lens, right? Or low light scenes, you need wide aperture. And when you have wide aperture, some parts of the image are really in focus, other parts basically get too defocused, right? Now, to balance this out, typically cameras have this thing called as dual pixel defocus blurring, which basically means that every pixel on the camera lens, you basically have a left view and a right view. So for every pixel, you have like two photodiodes, one receiving the light rays from the left view and the other receiving from the right view. You combine this information. So literally these cameras typically combine this information so as to get a more balanced focus, okay? So you could basically use Restormer as an algorithm to do this dual pixel defocus blurring, where the input is a defocused image and the left-right views from the two photodiodes per pixel. And you can observe, from this blurry image, the Restormer model is able to, still extract out the words very accurately. Okay. Last example. So essentially, how does it perform on image denoising? So here is the noisy image, and it's a small patch to show the kind of Gaussian white noise that has been added. This is a grayscale noise that has been added. And across these different models, you can observe Restormer basically really gives you the most faithful output. Okay. Here is again a noisy image where, if you basically zoom in, you basically observe that this is a Gaussian color denoising, the Gaussian color noise that is added. And this is basically the Restormer output with all the noise removed. Okay. Again, you basically see this is a noisy image. The same noisy image here, and there's some object here, but which is not visible because of the noise. But when you try to do Restormer-based restoration, you can actually see a real image in this real scenario, a good denoising performed. Okay. So in summary, in this video, I talked about image restoration transformer or Restormer. It basically is a 4-level encoder-decoder transformer-based model for image restoration, and it has a few interesting innovations. The most important one being the multi-depth-wise convolution-based head transposed attention layer, which is basically which has depth-wise convolutions and self-attention along the channel dimension rather than the spatial dimension, thereby reducing the quadratic complexity. I mean, thereby reducing the overall, latency for the model. It also has a gated depth-wise feed-forward network, rather than a standard feed-forward network, right? And while training, they also use this progressive learning recipe, which helps them train better. Okay, using various tasks. I showed how Restormer actually gives you better results. Now, obviously, there are better models in today's world, but Restormer is still a very important, a very important point in the history of image restoration. Okay, that's it for this video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.